Okay, and this is very important because once you know how things fail, you can design so that they never fail. Okay, so there are two questions we're interested in. One is why materials fail. And I think we've answered this question to an extent previously. And then how can we predict failure? And of course, if you can predict failure, then the next point is to use this prediction to design a material so that we are never close to that failure point. So why material fails, we've seen this. I'm not going to give an explanation on the microstructure and things like that. We're only interested in a empirical way of figuring things out. We basically take the material, we subject it to a tensile test, we make a plot of sigma versus strain. And then when we do that, we see there are pretty much two ways in which they fail. One is it's a ductile material, and it shows this curve I've shown on the left. There's a point called the ultimate strength. There is a point where yielding occurs. And then there's a point where failure occurs. Okay, this is for a ductile material. For a brittle material, we see that the point of failure, the strength rather, is the same. This strain, let's call that. So we know for the ductile material, SU, SF are distinct. And we know that for a brittle material, SF, SU are the same. That is, it doesn't really give you a notion it's going to fail. So clearly, when you want to talk about failure, you typically do this based on SY. Okay, SY is the point where things go nonlinear. It's a very safe way of doing it. You never really try to go to the maximum strength. So that extra buffer from SU to SY to SU can be used as a safety measure. So you never really design based on SU, just design based on SY. And here we are stuck with designing based on brittle materials are rarely used for things we care about, like bridges or homes and so on, because they really don't give you a chance to determine when failure, because they just fail. Now, there are cases where you want things to break intentionally, and I can't think of some of them back of my mind, but there are cases where brittle materials could be potentially be used. Maybe it's a safety measure. If you put it in an element where it will fail and give you a warning that other things are going to fail, maybe you would want to put a brittle material inside your design. But most of the time, you don't see too much brittle materials in going into your design. So we are going to look at theories of failure for brittle and ductile material. So there are 6 theories we'll look for and use for calculation. So these are theories of failure. There are some for ductile, some for brittle. Ductile material. There are 3 theories we'll look about and use and understand them and use for calculations. It's the maximum shear stress theory, MSS. Second one is distortion energy theory, DE. Third one is ductile Coulomb. Coulomb more theory, TCM. Then we have three theories for brittle materials. Maximum normal stress theory, M and S. Two, brittle Coulomb more theory, PCM. And then the final one is modified more theory, MM. Okay, so here's what the theory says. The material yields when the maximum shear stress equals or exceeds the maximum shear stress in a tension test specimen. Of the same material during yielding. Okay, just parse that in a bit, but this is what the theory says. Okay, so there are two things which I think are important. So what I'll do is I'll explain those things. So the material yields when the maximum shear stress. Okay, so what is this saying is in a general scenario where there is some material which is loaded, you need to first compute the maximum shear stress. So let's assume that there's some material, it's subjected to some complicated loading, moment F, F1, F2, and so on. So what you'll do is you will take this and you'll compute max shear stress. Okay, this is tau max. How will you compute that? Well, you know how you can do that with Morse circle. If you can identify the critical point and you can draw the stress element, then you can compute the maximum shear stress using Morse circle. So that's the first part. So this is some, for whatever loading you're considering, you should first do that. You should compute this for that loading. Now, that's part one, that is the computation for the loading. You need to compare this against some benchmark. The benchmark here is the maximum shear stress in a tension stress specimen of the same material during yielding. Okay, what it's saying is you also need to run a parallel experiment where you will take the same material, subject it to a tension test. Okay, so when you keep increasing sigma, at some point Sy, this material will break. Or yield, sorry, yield is a better word. Okay, so we've done the tension test experiment. The only thing left is we need to compute the maximum shear stress in this experiment. Again, how do you do that? Well, you'll again use the Mohr circle. So this is the 2D element. It's subject to stress sigma. Okay, there's no shear stress because it's a uniaxial loaded specimen. There's no stress in the y direction because again, there's no load in that direction. It's only uniaxial stress. So this is the stress element. From the stress element, we can also draw a Mohr circle. So if you know that this is sigma equals 0. So one stress is 0. One stress is sigma, which is Sy. You've got 2 points on the Mohr circle. You take the midpoint, which is easy. You draw a circle. Okay, clearly this point is Sy divided by 2 comma 0. The radius of this circle is clearly, just from the figure, Sy divided by 2. But this is also the point where the maximum stress occurs, right? The maximum stress is at right angles or 90 degrees here to the horizontal. So in a simple tension experiments, we know that the maximum stress is Sy divided by 2. Okay, so now we have 1 and 2, and we only need to do the third part, which is equals or exceeds. So we take this stress, tau max. When this stress equals or exceeds Sy divided by 2, which we computed here, we have the failure criterion. So that's all we check. This comes from the loading. This comes from Mohr circle, and there you have what you're after. Okay, now that we've understood the theory and what it means to compare, let me just tell you how to do this for a 3D case, because you'll be solving problems. So how to apply the theory in 3D. Okay, in 3D, you'll have 3 stresses. Let's call that sigma A, sigma B, sigma C. Okay, so if you have 3 stresses, you can actually draw 3 more circles. So you'll see, you'll always get this case where you'll have 2 small circles and a big circle, and the 2 small circles will be inside the big circle, no matter what the problem is. Okay, so what I've done here is I've renumbered these stresses, sigma 1 greater than sigma 2 greater than sigma 3. This is sigma 1. These are the principal stresses, by the way. This is sigma 3. This is sigma 2. Okay, clearly this is the maximum shear stress for the in-between circle. This is the shear stress for the smaller circle, and this is the stress for the larger circle. This is happens to be your critical stress. This is tau max. This is the failure which will determine failure. It won't be the smaller stresses because they have a smaller value. just do one more thing here. Let's just call this so that it's all complete. Let me call this tau max prime. This is tau max prime, so you don't confuse it. So this is tau max, but let's call this tau max prime. The prime here indicates it comes from the loading condition. Okay. Yeah, so here tau max prime. Okay. So now we have tau max prime. We know what the value is actually. Tau max prime is nothing but, remember that the radius of this circle, the biggest circle, is sigma 1 minus sigma 3 divided by 2, right? Because sigma 1 minus sigma 3 is the diameter. So half of that should be the radius. So all we need to do is we need to set this to be greater than or equal to Sy divided by 2. This is where failure will occur. So the formula for failure using this theory is that sigma 1 minus sigma 3 is greater than or equal to the yield strength of the material. This is something which you get from the simple stress strain curve for a uniaxial testing condition. Sigma 1, sigma 3 will come from the specific problem by computing these stresses, essentially principal stresses. Next is how to use this for design. Okay, we can define the factor of safety, ND or N. This is basically factor of we've seen this before, design factor or factor of safety, depending on when you calculate it, before or after design. So you'll write this as max shear stress upon allowable stress. That would be tau max divided by tau max prime divided by tau max, which will be Sy divided by 2 divided by sigma 1 minus sigma 3 divided by 2, which is the same as Sy divided by sigma 1 minus sigma 3. Okay, well, why you can afford to do that? It's because for a ductile material, the material doesn't fail at Sy. It fails at Su. So you could actually take that difference between Sy and Su to put in a factor of safety. So you can actually go some orders of magnitude higher than Sy, because Sy is not where the material failed, it only yields. Ultimate strength is much higher than that. Yeah, I think this should be swapped. Let me see. So we've said that this is tau max. This is the maximum possible stress this material can take before it breaks. And then this is the tau max with the apostrophe is basically the loading. So clearly you cannot exceed this stress, because then it will break. So I think I switched this. This should be, correct this. This should be tau max, and this should be tau max with a prime. Okay, so tau max, which is given here, is Sy divided by 2. And then in the case we're looking at, which is the loading you will be considering, whether it's safe or not, you will divide that quantity, and that should be this. So just make this correction. This is the maximum shear stress in the uniaxial case, and the one in the denominator is the one which is the loading condition. So given that two stresses, we can compute the factor of safety or the design factor, depending on if it's before the design is done or after the design is completed. Okay. Now, I said that the stress is always three-dimensional, but we've looked at cases where the stress is two-dimensional. So for 2D case, that's something we've always considered. That is, there'll be a plane stress element, there'll be two stresses. So how do we reconcile the fact that stress is always three-dimensional? Well, if it's a 2D problem, then one stress is always 0, and that's how you can reconcile the two. Okay, which means that, so to give you an example, let's say that it's a plane stress element and you are told that the maximum stresses are 5 MPa. I'm just not going to put units, not very important here, and let's say 3 MPa. Okay, so this is like, say, a plane stress element with principal stresses sigma A, sigma B, and shear stress is clearly 0 because those are the principal stresses. Okay, so if you're given this, you still need to compute the biggest Mohr circle. So how do you do that? Because you only have 2 stresses. Well, the third stress, we'll assume it to be 0. Once you assume that, what you'll do is you number them, these stresses, such that, so number the stresses as sigma 1, sigma 2, sigma 3, such that sigma 1 is greater than sigma 2 is greater than sigma 3. So clearly, sigma 1 in this case is 5, or sigma 1 is sigma A. Sigma 2 is the next stress. So here it's going to be sigma C, which is 0. We just put that 5. And then finally, the third stress, sigma 3, the least stress, is sigma B, which is minus 3. Okay. With this information, you can actually draw the Mohr circle. You could also, instead of doing this step all the time, you can just skip this and just say 5 would be the max stress, 0 is the next stress, and minus 3. That's just saying this is sigma 1, sigma 2, and sigma 3. Okay, so to compute the biggest, the value for the, let's say, factor of safety, or n, it will be Sy divided by sigma 1 minus sigma 3. So now you know that sigma 1 is 5 and sigma 3 is minus 3. So you can then do the calculation. So it will be something like Sy divided by 8. So whatever you've given as Sy to be, you can compute the factor of safety. Now here's another case, just to give you how this works. So example 2, let's say that the stresses, the principal stresses, are sigma A equals 5, sigma B equals 1. So it's a 2-dimensional problem. So you will assume that the third stress is 0. So now we rearrange such that sigma 1 is greater than sigma 2 is greater than sigma 3, which gives us 5 is greater than 1 is greater than 0. So clearly, this is sigma 1, this is sigma 3. And then if you are told to compute the factor of safety or design factor, that will be Sy divided by sigma 1 minus sigma 3. And that is, this is clearly 5 and this is 0. Right? That's here. So this is going to give me Sy divided by 5. Hello. Okay, we can continue. Okay, so just remember that if you had not taken this value, you would get the wrong answer, right? Because you would then take 5 minus 1, thinking that that's the max, that's the minimum. That's simply not true. The minimum stress here is happens to be 0. Okay, so be very careful when you solve problems. This is what you need to do. You need to consider the 3-dimensional Mohr circle, not the 2-dimensional Mohr circle. Okay, now let's, I'm going to go a step further and then draw the shape of the failure region for a 2D case. And it will be clear in just a bit. And this will be useful later on when we compare different theories. So 2D case, as I said, there'll be 2 stresses, but we will always assume that the third stress is 0. So we can have the following cases. Okay, we have sigma A is greater than 0. Sigma B is also greater than 0. Okay, and then clearly the sigma, clearly in this case, sigma 1 is either sigma A or sigma 1 is sigma B. Why would that be? That's because these stresses are
positive, and they would be, one of them will have the maximum value. But always sigma 3 would be sigma c, which is 0, because it's the least stress. Now, in this case, when you look at failure, the failure criterion is what? Is tau max is greater than or equal to sy. So let's just consider the point where failure occurs. That will be tau max equals sy. This will happen when tau max, which is sigma 1 minus sigma 3 equal to sy. So this could either be sigma 1 is either sigma a, sigma 3 is clearly 0. So it's either sigma 1 equals sy or sigma a equals sy or sigma b equals sy. This depends on if sigma a is greater than sigma b, or the second case will be when sigma b is greater than sigma a. But it will always be one of those two equations. So this is the failure for this condition. Okay, next you can look at this condition: sigma a is greater than 0, is greater than sigma b. Okay, in this case, it's clear that sigma 1 is sigma a, that's the biggest stress. And then the smallest stress, sigma 3, is sigma b. Okay, in this case, the failure will occur when sigma 1 minus sigma 3 equals sy. In other words, we could have either sigma a minus sigma b equals sy. Just circle this. Let's just call that 1. This is my second condition. 2. You could also get a case where sigma b is greater than 0, is greater than sigma a. This is just going to switch the values of sigma a and sigma b. It's very similar to case 2. We'll have sigma p minus sigma a equals sy. That's condition 3. And there's one more which we missed, which is what if sigma b and sigma a are both negative? So this is the third case. The fourth case, where 0 is greater than sigma a is greater than sigma b. In this case, sigma 1 is clearly 0. Sigma 3 can be sigma a, or sigma 3 can be sigma b. And that just depends. If this is the case, then you would have this condition, but you could also have this case. Sorry, my bad. This should be sigma b. This should be sigma a. This is the other case. But the first stress, sigma 1, is always 0. So in this case, failure could either mean sigma, which is sigma 1 minus sigma 3 equals sy. So the first case, we have sigma b minus, sorry, sigma 1 is 0. So 0 minus sigma b equals sy, or 0 minus sigma a equals sy. So this is here, or it could be this, which goes here. So the two conditions are sigma b equals s minus sy, or sigma a equals minus sy, and this depends on which of those are greater than the other. So let's call this one as, these two as 4. Okay, so we have generated 4 conditions just for the 2D case, depending on the values, magnitude, and signs of sigma a and sigma b. Now we can actually do this thing, which is plot these values on a curve involving sigma a and sigma b. Okay, let's just do that. So this step is plotting equations 1 through 4. Okay, and I'm going to do is would draw the axis sigma A, sigma B. Okay, first let's look at the positive value. So this is when sigma A and sigma B is in the first quadrant. So we need to plot the contours such that sigma A equals Sy, sigma B equals Sy. So we can see that in the first quadrant, sigma A, let's call that Sy. See, this is Sy. Okay, so these are equations 1 now plotted on the sigma A, sigma B contour. Now the other one which is easy is perhaps this one. Sigma B is minus Sy, sigma A is minus Sy. This is when both sigma A and sigma B are negative, which means they are in the first, second, third quadrant. So go here, plot minus Sy, minus Sy, and then just join these lines. So these are equation 4. So those are the easier ones. The harder ones are probably equation 2 and 3. Let's look at 2 and 3. So for 2, we have this equation, sigma A minus sigma B equals Sy. So if you remember the equation for straight line, this is basically the equation of a straight line with the equation of the straight line x divided by a plus y divided by b equals 1. This is basically the equation of a straight line such that it passes through a and b on the x and y axis. So if you take it in that form, if you divide the whole thing by sy, this will intersect the x-axis or sigma a axis at sy and sigma b axis as at minus sy. So plus sy for sigma a, which would be this point, and minus sy for sigma b. And so it will be this line. So this is number 3, sigma a divided by sy minus sigma b divided by sy equals 1. You can see that the intercept is sy, positive, and intercept is negative sy for b. Okay, and the last equation is this one, sigma b minus sigma a is sy. So the x-intercept is, sorry, the y-intercept sigma b is plus sy, which is this, and the minus intercept and the sigma a intercept is minus sy, and so this would be this line. This would be number, my bad, this should be 2. This should be 3. This is sigma a divided by, see, it's sigma a b. I'm going to write it this way. Okay, so this region is the safe region. Okay, it's the region where there is no yielding, which means that as long as your sigma a and sigma b, the principal stress, is anywhere on this yellow region, your design is considered to be safe. If it's outside, it's going to fail. Now, if you want a factor of safety, then what will happen is this will actually shrink. It will become something like this. This is if you add factor, if you add safety, it will shrink, which means that now your safety contour is even more conservative. You can only be in this region. If you go out, it's still safe, it won't fail, but you don't know when it will get to this point where failure occurs. So this, I think, is a great way of visualization. Once you have this plot, it's all a matter of plotting sigma a and sigma b on this
on this graph, and if it is inside the yellow region, it's safe. If not, then it's not safe. So this is the maximum shear stress theory